So let's do this example. So we need to first identify the system. So so a block of mass 10 kg starts at the point A at a height of 2 meter above the horizontal and slides down a frictionless incline. It then continues sliding along the then it continues sliding along the horizontal surface of the table that has friction. The block comes to rest at point C, a distance 1 meter along. So it started at rest and then it stops here. So it might be that it stops because we can agree that at this point it has friction, but it moves until it stops here. It stops here due to the friction. So friction pulls it this way. So friction pulls it this way, and then it wants to go that way. So it ends up stopping at some point. So at some point here, it stops. So I want you to get that because I will be very helpful. So ignoring the small transfer of energy, so ignoring a resistance. So the reason we ignore, they say must ignore a resistance. This is to uh, make it a point. This is to make it a point that then energy loss will be here due to the friction. The energy loss will be here due to the friction instead of air, instead of reducing due to bumping into air and all that. So now, so we need to identify. So this is a system. Okay, maybe let me. Uh, this is a system. This is our system. So our system. So our system is the block plus the table. This is our system. So we don't care of anything outside this system. We just care everything happening at this circle, at this circle. We don't care of anything else. So this is our system. So now, so that and this is so this is why even you have a reference point here. So the reference point is within the system. So now let's calculate the energy of this system. So this will be the internal energy of the system. So okay, let's go here. So here they say there's a decrease in potential from A. Yes, okay. When an object is higher there, it has a higher potential. So due to the high height, and then when the height decreases, so does the potential energy. So and it moves from A. When the block moves from A to B, so it started uh, decreasing in potential energy. Yet at the same time increasing kinetic energy because it start moving. So it's moving, gaining more moment, gaining more speed, and then so then it gains kinetic energy. And then from point B, from point B, the from point B, uh, the kinetic energy started to decrease, and there's an increase. There's an increase in internal energy from B to C. So increase in internal energy from B to C. will help us to identify now that we need to use the form when calculating energy. We need to use this form of energy where we have the change of potential plus the change. This is where we involve physically, where we involve internal energy. So this would be change in potential energy plus change in kinetic energy. So this will be the total energy of the system. So now the internal energy of the system. So now we have to, okay, initial. So here the initial, let me call it ui, is 0. Oh, the final, actually this will be the final because it moved, okay, here. So here at this point the potential, as the block moves, or it moves at this point, it has a final potential of 0, yet it has an initial potential energy of mgh, which is the height. So this means that the change, in potential will be mgh. So we'll have this contribution, and now we'll have that okay, because let me draw this reference point again. We started, okay, so since this object started at rest and then it stopped here, this means that the translational kinetic energy would be 0. So we have 0 here. So then we have that the total energy would be mgh, where we can then substitute the values. So this is where we come up with this equation. This is where we come up that increase in internal energy of the block and the table is this. So it means that this is a total energy we're talking about, the total energy of the system, or the total energy of this system will be this one. So it will be the mg, which will be actually the 200 joules. So it will be the 200 joules. So let's continue to the next problem. So now in this problem they say a bowling ball at rest has temperature of 18 degrees, and then the ball is then rolled down the alley. So we have a ball at rest that has a temperature of this, and the ball is rolled down in an alley which is very horizontal. It's very horizontal. Is horizontal. So, and then they say that ignoring the dissipation of energy by friction, it means that it's frictionless, the flow is frictionless, and drag forces, that means we ignore air resistance, is the internal energy of the ball higher, lower, or same as when the ball was at rest? So is the temperature of the ball higher, lower, or same as when the ball is at rest? So here they say a remark, a change in internal energy of a system. A change in internal energy of a system does not always cause a temperature change. The internal energy of a system can change while the temperature of the system remains constant. For instance, when an ice melts. So when an ice melts, this is actually when there's a phase and transition where the ice changes from solid to liquid. Yes, it is still 0 degrees, still maintain at 0 degrees, yet there's a change of its state, and it means that there's a change of its in because the in the internal energy of a solid ice is different from a of solid water is different from the internal energy uh, of uh, of of liquid water. And we know that the the molecules are more freely in water. The water molecules are more freely in a liquid form, and while and they are not that free in uh, in a in a solid state. So the internal energy changes. So then, so let me continue. So okay, let's go over the solution. So the only change, so they say that the only change is that the ball is now rolling. That's the only change. It was addressed and now it's rolling, and it has a macroscopic translation in rotational kinetic energy. It's, it moves oh, and it's rolling. It's rolling. So this is the this is what they mean by microscopic translational and rotational kinetic energy. However, the definition of internal energy does not include the kinetic energy of molecules due to translation or vibration of a system as a whole. Therefore, the internal energy of the ball is the same. The temperature is associated with the average translational energy due to individual motion of the molecules in the temperature is still 18 degrees. Okay, maybe let me explain this. So here, I hope you recognize that here now we're talking of the ball as a system itself, not a case where we talk of a ball and a floor. If we were talking of a case of a ball and a floor, this could be a different story. But now we are considering the ball as a system itself. So we are concerned of its temperature. The temperature at rest was 18, and then even when it was rolling, uh, it was still 18 due to the other external factors that we ignored, the of friction and all the other friction and air drag and friction. So, and remember now we are talking of, because when we talk of temperature, when we talk of a temperature, we talk of the molecules, talk of micro. When we talk of temperature, we talk of a micro. We talk of microscopic particles. So we talk of the average of the, when we talk of temperature, actually we talk of the average kinetic energy of those molecules inside the ball. So, or part of the ball. So we talk of that when we talk of temperature. So here we're dealing with a microscopic situation. This, and then by the definition of internal energy, you know that we have to ignore the macro, or the macro, in this case, what is outside the system. So the macro, we need to ignore the macroscopic situations. So that's why it doesn't matter whether the ball is rolling or it's moving in whichever way. So that's why there is no contribution due to the translational rotation. Uh, the macros here, the microscopic translational and rotational energies. So the temperature is the same. So there will be no change. I think the answer would be that actually temperature kinetic due to the temperature will be the same, and what are we required to find? Okay, the ball is then rolled. Is the temperature of the ball higher or lower or the same? It's the same because there is no increase, in the internal energy. Remember that there is no increase in the internal energy because the effect of the macroscopic does not affect the microscopic. So remember that the ball, or the molecules in the ball, and these are the internal. This is these molecules that contribute to the internal energy, and this is why we talk of temperature, which is the average kinetic energy of these molecules. And then, since there is no change, in E, then there's no change in E int, and call it E int, the internal energy. So there will be no change in the temperature. So thus there will be no change in the temperature. But if, say, there was a change, or it was an increase, maybe there was a heat applied here, there was a heat, or any change actually. Okay, the heat is due to the average kinetic energy. So let me not. So if there was an increase in kinetic energy of, if there was an increase of kinetic energy of the molecules inside, so this means that the average of the kinetic energy will increase, and then this means that the temperature was going to increase as well. So there was going to be an increase in the internal energy. So I hope this is clear as well. So now maybe okay, I've explained this part, so I don't know whether to start this part. Okay, so let's go to maybe reading. So heat, let's talk about heat now. So definition of heat. So heat is the energy that flows from higher temperature object to lower temperature object because of the difference in temperature. So we talk of heat. Okay, maybe. So heat is the energy transfer. So the any so here, from a higher temperature, let's call it T, say T1 and then T2. So where T1 is greater than T2, so there will be so energy is the heat is the energy that flows from higher temperature object to lower temperature object because of the difference in temperature. So let's say if object A is hotter than object B, and then the heat will be transferred, the heat energy will be transferred from object A to B, and to such a point where they reach equilibrium, if I can say, where now the temperature is averaged. So that's the whole purpose of this. So and then there's temperature difference here. There's a temperature difference between the two objects. This one is higher, A is higher, it's hotter, and B is less hot. So now there is a change in temperature here. So then there will be energy transfer due to the difference in the temperatures. So and the SI unit of heat is joules. Direction of heat flows spontaneously. So heat flows spontaneously from a system at high temperature to one at low temperature, and it originates in the internal energy of the hot substance. So due to the high maybe internal energy of object A, it will then uh, uh, transfer its heat energy to another system, which is B. So note, it is not correct to say that a substance contains heat. So they say that it is not correct to say the substance contains heat. So the substance contains internal energy. And then heat is a quantity. If you can think heat as a quantity of work, you cannot say that an object contains work. But when an energy is delivered, or when a force, actually when a force is delivered at some distance, and then we talk of work. The same, when we talk of energy transferred to an object, then we talk of heat energy. So we cannot say that an object has a work, and it's the same as we cannot say an object substance contains heat. It can transfer heat energy. It contains internal energy. So let's talk about heat. Oh, this is what I was talking about. Heat and work. Heat and work are similar. So heat and work are similar in that both describe a particular kind of energy transfer. Yes, we talk of energy transfer. So heat is an energy transfer. So work is an energy transfer due to a force acting through a displacement. Heat is a microscopic form of energy transfer. So this is very crucial. Energy transfer involving large numbers of particles. The exchange of energy occurs due to the individual interactions of the particles. So no macroscopic displacement occurs when heat flows, and no macroscopic force is exerted by one object on the other. A system can possess energy in a various form, including internal energy, but it cannot possess heat or work. It cannot possess heat or work. So due to they are just heat transfers. So heat and work are two ways of heat and work actually are two ways of transferring energy from one system to another. So just take note of that. So maybe okay, this will make a separate video and then complete all this as a okay. Let me see. Okay, need to complete everything. So let's talk of let's go over this experiment. So in an experiment similar to that done by Joule at the bottom, an object, so an object of mass m, of mass 12 kg descends a distance of 1.25 meter at a constant speed while causing rotation of a pedal wheel in an insulated container with water. If the descent is repeated 20 times, what is the internal energy increase of the top of water in joules? So this will be the potential energy, or the change in potential energy, where we have mg, and then remember that okay, uh, so here we have that the mass descends a distance of, this is a particular scenario, or I would say I don't know where to put it. This would be, let's say this is the way you do the experiment, or this is, and then where here you can repeat, when you repeat the action, say let's say this will be the action, this will be the action in the experiment, and then when you repeat, now when you repeat this, when you repeat this action 20 times, that's why they multiply it here. So they try to multiply it here to, just to show that. So they try to multiply this distance like this. So because this would be equivalent to doing This will be, if you do this, uh, if you do it often, or if you do it several times, this is equivalent to multiplying uh, the distance by the 20, or the number of times you're doing it. So now they have this as their potential energy. They say that if all of this energy goes into water, if all this potential energy goes into water, the internal energy, so if all this energy goes into the water, so the internal energy increase of water will be this amount. It will be this amount. So I think you recognize that this is the system. This is the system, and this is a clever way of this is a clever way of affecting. This is the clever way of using external uh, of using the external to affect the internal. So we want to find the amount of, or because this is delivering work here, or potential chemical, yeah, this is delivering the potential energy the inside the system. So this is more of increasing the potential energy in the system, and then we'll find out what is the increase in the internal energy of the system. So in as much as you can see things outside, 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 and outside, but when you note here, we and then when we talk, we are not concerned what is being here, what is this side. We are concerned of what is the energy delivered here, what is the energy or the potential energy due to inside this box, due to inside this box. So this is a very clever experiment, if I may say. So that's why we can say now this will be this potential which is being delivered in this way. Now we can say that this is be the internal energy increase of the water. So now let's talk, let's go here, heat capacity and specific heat. So heat, if you talk of heat supplied or heat removed, okay, heat supplied or heat removed in changing the temperature of a substance. So the heat that must be supplied or removed to change the temperature of a substance is given by this equation, where we have mass times the specific heat. So a specific heat is a quantity that is specifically for a medium, certain medium, and it can be found experimentally. So you record it from an experiment, and then actually there are many objects they have the specific heat known. So and then the delta T will be the change in temperature. So note the equation Q is equal to mc delta T applies when no phase change occurs. So let's say maybe we are concerned maybe then transfer. Okay, maybe I may not complicate by adding several mediums. So we talk of water, heat must be supplied or moved through it. So when we talk of water, maybe and the walls, or the walls, say the walls are made of I don't know, maybe they're made of copper. So we'll be concerned of the energy transfer, or the energy taken by the water. So in fact, when you cook, yeah, when you cook, this is very fun. When you cook, uh, the energy is transferred from the walls of the pot into the water. So we can calculate that, because we know the specific heat. We know that we will know the specific heat of water. So you can calculate the energy transfer or energy be supplied, the energy that must be supplied into the water to maybe to boil it or to change the temperature. So now sometimes we find that we want, let's say we have a hot water now. Let's say now we have a hot water and want to know the energy transfer to the pot. So let's say you have a hot water, you pour hot water into a pot, into a cold pot, and then you want to know the amount of energy that would be transferred into that pot. So in that case, you need to find uh, the specific heat. So let's call it CC, the specific heat of uh, of this. We say maybe a copper or a copper pot or something. So you'll use that here and calculate the energy transfer. You'll know the temperature. The temperature of the pot, maybe it would be 0, and the temperature of the water would be 100. So you know the temperature difference, and then you'll calculate the amount of heat that that would be supplied to that to that pot to 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 make it hot, or to 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 make the two to be balanced, to be at the same temperature. Maybe you find that they go to equilibrium maybe at 40 degrees. They both 40 degrees, and then there's no energy transfer. They'll both be 40 and 40. So this is a very interesting topic. So you must memorize this equation. You must know this equation actually. For that's equation for heat. So this is what I was talking about. So specific heats of common substances. So you'll be given this. Don't worry about it. You'll be given. But most things like water are very basic. You should know them. And ice, they're very common. So, but I think they will give you this information. So now let's go over an example. So in a half hour, a 65 kg jogger can generate this amount of heat. This heat is removed from the body by a variety of means, including the body's own temperature regulating mechanism. If the heat were not removed, if the heat were not removed, calculate how much will the body temperature increase. So specific heat capacity of a body tissue average would be this. So we're given this, the C. So, and also, or we want to find the temperature increase. So, or the change in temperature. And then we are given the energy. So we're given Q. We are given the heat, the energy here. So we're given that the energy of the heat. Then you can, the only unknown we have is the change in temperature. So we rearrange to make change in temperature as the subject of the formula, and then you can solve. Actually, here uh, you'll get, because we're dealing with, as you can see, there's a K here. We're dealing with kelvins, so you'll get your answer in Kelvin. So here they then converted it to degrees. So I think, but I will check. But I think it's 273 plus, I think plus K or something, if I'm not mistaken. That's way a formula to find degrees. So is it negative? Maybe negative, I'm not sure. I'll check. So but I think the formula maybe a very Accurate one would be like this: Kelvin is equal to degrees, like this. So this is how you can convert into degrees. The vice versa, when you want Kelvin, maybe they're giving you degrees, but with this formula you need to work with kelvins. So if they given you degrees, if they given you degrees in the problem, so you need to convert it into Kelvin. So you will use the same formula and make a Kelvin the subject of the formula. You can simply say that kelvins is equal to degrees Celsius plus 273.15. So then you'll find kelvins this way. So what I normally okay, recall this formula, and to recall this formula, I know that 0 Kelvin is I think it's negative 273.15 degrees. So that's why I know that if I plug in 0 here, I must get that the degrees are this. So this is how I recalled the formula. So let's go to the next example. Check if I can do, okay, then I'll stop here. So if I go to the next example, so they say here, calculate the work that an object would this, you need to convert this into degrees, into kgs, of this mass can do as a result of falling. Calculate the work, calculating work now. Calculate work an object with m can do as a result of falling a distance of 3 meters. All right, then B, assume that the object falls into 10 liters of water in an isolated beaker. If the entire kinetic energy of the object is converted to thermal energy, calculate by how much does the water temperature rise. Hint: the specific heat capacity of water is 4186 joules per kg Kelvin. The density is 1 gram per liter. So then they given you the conversion where 1 liter is equal to 1000 cubic centimeters. So now the solution is, so they want us to find the work of an object of 0.4 kg which is falling down a distance of 3 meters. So here the potential energy, I'll just read the solution as it is. The potential energy of falling, the potential energy of falling decrease while the kinetic is, so the potential decrease when the thing falls, the potential energy decreases while the kinetic energy increases. Therefore the potential energy lost is equal. So yes, so the potential, this is what they say, that so the potential the potential energy loss is equal to the kinetic gain. So when an object is here, is on top here, and it has a potential energy u, and then if you take an object high here, and then it will have a potential energy of u. So and then when you leave it to fall, it will increase in kinetic energy, and then when it reaches this point, so it will increase kinetic energy. So it will increase in kinetic energy. So when it reaches this point, the ground, from top, it will have this kinetic energy the same this kinetic energy will be the same as the potential energy. It will have gained the same amount of energy that it had due to the potential. So that's why you say the potential energy loss. So the potential energy loss is equal to the potential kinetic energy gained. So I hope you see that. So it means that the change in kinetic energy is equal to the change in potential energy. So therefore, it will be mg change in height, which is this. So this will be the change in kinetic energy. Then the work done, is equal to the change. Remember that. So remember the equation where work done is equal to the change in kinetic energy. So remember what it was a work energy theorem or something. So this would be so this means that the work done will be this. This would be the work done. So the entire kinetic energy of an object is converted from the statement, from this statement where they say um, where they say it's converted over here. So the entire kinetic energy of an object is converted to thermal energy. So now since that we have the kinetic energy, and then we can use that from here. The kinetic energy of an object is converted to thermal. So this means that the kinetic energy will be equal to Q, which is the thermal energy. Then this will be like this. So we have that. So in B, what is required of us in B is that assume that the object falls into a 10 liter of water in an isolated beaker. Okay, so we need to calculate by how much does the water temperature rise. So we need to calculate by how much does, so we need to solve for, so now we have the Q, so we need to solve for the change in temperature. So but we don't know the mass, so we don't know the mass, but we're given density. And then yeah, we're not given mass, because here in this equation we need to plug in mass, but we're given density. And you know this formula that say mass, density is mass over volume. So you can rearrange and make the subject of the formula. This is what I did here. So then you can then substitute the density times the volume, and which we are given, that is 10 liters. So this is the part where instead of mass we plug in this part, and then we are given, and then since we are given the heat capacity of the water, which is this, and then we plug in, and then we get that this will be the change in temperature. So this is in Kelvin. So I don't, so we can leave it in this because the Kelvin is the SI unit, and then you can leave it in this form unless they've asked that we must leave it in degrees. Then that's where you'll say because what is the relation is 9, so you need to 73.15 plus Kelvin is equal to 0 degrees, so it's equal to a degrees actually. So then you then plug in the this here. So we plug in this here, and then we'll get the degrees. So you remember it's a negative here. So we'll get the degrees here, temperature in degrees. So let's go to the next example. So the next example here, we have that a saucepan containing 5 kg of water initially, 5 kg of water initially at a temperature of 20 degrees is heated over a gas burner. So it's heated over a gas burner for 10 minutes. The final temperature of the water, so the final temperature of the water will be is 30 degrees. So what is the internal energy increase of the water? uh, so what is the equation is m. See, and then we have the change, and we know we can check from data what is the heat capacity of water, and then we are given this, and then we can find this from, because it changed from 20 to 30, you can find that, and then you can solve for this. B, what is the expected final temperature if the water what is the expected final temperature if the water were heated for an additional, so if it was heated for an additional 5 minutes. All right, so see, is it possible to estimate the flow of heat from the burner during the first 10 minutes? So let's check what they did here. Oops. So let's do A. Remember, we can do A. So here we are interested in the internal energy and the temperature of the water. So we define a system that contains, so we're interested in the internal energy and the temperature of the water. So we define a system that consists of water in the saucepan. So that will be our system. Although the pan is also heated, it is not part of this system. So the same as the box. So we're interested in the part that is inside, not the box, but what is inside the box. So this would be our system. So the pen and the pen and the room are all outside the system. So all right, so now, so the change in temperature, this would be this will be the degrees, and then I'm not sure why they put 10 Kelvin. Okay, maybe you can calculate and check if you get oh, okay, it's a very it's a very simple thing. So look, when you get 10 Kelvin, you just need to convert this and convert this. So 27315, so you add, oh, so in this case you add, because you want Kelvin, so it means that we need to add instead of subtracting. So say 30 plus 273.15. This is our final temperature, and this would be initial temperature. So then you need to subtract it, and then you need to subtract, okay, you need to subtract this, by 10 or by 20 plus 273. So you can see that this is actually when you're multiplying, so this, when you can check correctly, this so this will cancel this, so it will be the same as 30 minus 20, which is simply 10. So this would be, that's why it's 10 Kelvin. So this will be 10 Kelvin, and then the energy, or the change in internal energy. So this would now would be the internal energy, so which is equivalent to the thermal energy of a system, because we talk there's no additional energy than the thermal energy, or the energy due to the what is inside the system, or in this case our system is the water which is inside the saucepan. So now this will be equal to this. So you are given the mass, you are given the heat capacity, and we've calculated the change in temperature. So now we have what it would be our internal energy. So now let's go to B. So what was B? Okay, in B, what is expected what is the expected final temperature if the water were heated for an additional 5 minutes. So if we add 5 minutes, so we assume that the heat delivered is proportional to the elapsed time. So we compare to the heat delivered to time. So let's say if at this time a certain amount of energy was delivered, at this time a certain amount of energy was delivered. So if we use that method, then we can then even calculate if an additional time was added. So the temperature change, so we'll say that the temperature change is proportional to the energy. So the temperature change is proportional to the energy delivered. So if a temperature, so you can even from the formula, Q is proportional to change, because the mass and the capacity are, are constants, or some things that will not change. So the energy delivered will be proportional to the change in temperature. So this is the statement what it says. So if the temperature change, if the temperature then if this temperature changes, uh, if the temperature changes 10 degrees in 10 minutes, so if it changes 10 degrees in 10 minutes, it changes an additional, so if the temperature changes 10 degrees in 5 minutes, it means that it changes an additional uh, 5 degrees. It changes an additional 5 degrees in an additional 5 minutes. So this statement, it changes in additional 5 degrees in additional 5 minutes. But let's just do the maths here. So if the temperature change is such that is in a ratio, say that okay, let me use let's say in a ratio of this is in a ratio of 10 degrees is to 10 degrees is to 10 minutes, right? Then because we want the additional temperature, we're given the additional time. Let me check if I'm not mistaken. We're given the additional minutes. So maybe let's, okay, let me do it this side. So this is how we can do. So we know that the additional energy is proportional to the change in temperature, and we know from the problem that the ratio in which we can identify here, the ratio is that the change, okay, maybe so we have that, how many degrees, let me check, 10, the difference, or the change, which is the change in temperature, which is 30 minus 20, which is 10 degrees. Yes, 10 degrees. So the ratio is 10 degrees. So the change in temperature happened at 10 minutes, and then we want what is the expected final temperature if the water were heated for addition. So we want for we want now that degrees when an addition of 5 minutes is added. So now we given that 5 minutes is added. So now we'll cross multiply here. I hope I'll get the right expression here. So here we'll have this will be 10 times 5, which is 50, and then divide by, okay, this would be 50 minute degrees, and then this would be 10 minutes, and then the minutes would cancel the minutes, and then we're left with 5 degrees. So in the 5 minutes, 5 degrees was added. So let's go back. So now we've calculated it in this way. So let's go to how they did. Okay, so yes, this is the same thing. So it changes in additional 5 degrees in 5 minutes. So the final temperature, will be, what did I find the final temperature? Because the initial temperature will be okay. So it would be, instead of 10, okay, let me do this. Three 5 minutes here, so it would be 3 times 5 degrees. Okay, we have 3. Okay, maybe in 5 minutes, how many 5 minutes do we have? We have 3 5 minutes, and then we know that each 5 minutes, it's, so we know that each 5 minutes is 5 degrees, then it should be 3 times 5 degrees, which is 15 degrees. So that's why they added the 15-degree here. So that's why they added the 15-degree here. So that's why the total is this. So now say, is it possible to estimate the flow of heat from the burner during the first 10 minutes? So not all of the heat flows into the water. Heat always flows from the burner into the saucepan and into the room. All we can say is that more than 209 kg of the heat flows from the burner during the 10 minutes. So this is the one. Okay, this is the one calculated if you assume that all the heat flows into the water, and because we know for a fact that not all the heat flows into the water, so this shows that more than this actually flows from the burner during the 10 minutes, more than this, because this is just a fraction, some fraction of that heat, which others go to the water, others go somewhere else. So we're able to calculate the one which went into the water. So here I'll make a separate video for heat capacity, specific, here is specific heat. So here I'll deal with this separately.